Alright. So, now the question is okay, well, it seems like all along we have been working with an ideal transistor model which does not exist anyway. So, we now go back to all our circuits and start figuring out what this finite. Earlier the transistor was an was an ideal incremental voltage controlled current source, meaning that the output impedance was infinite. Now, it is not infinite after all, there is some R. Remember one thing in life and in engineering, right, nothing which is supposed to be infinite will be infinite, okay, alright, and nothing which is supposed to be 0 will be 0, correct, and both are consistent, correct. If you had a perfect 0, then 1 by 0 is infinite. So, you have a perfect infinity, that is not possible, right. So, nothing in the world is 0, nothing in the world is infinite. So, now we go back to all our circuits that we started off with and then see what happens when you have finite output resistance. So, fortunately it is pretty straightforward. Let us start with the common source amplifier, which was the first amplifier that we talked about. The incremental picture looked like this. This was RL, and ideally the incremental gain was what? Ideally, what was it? Minus GMRL times, so the output voltage was minus GMRL times Vi. Now, what happens? We have an extra here, which is a part of the transistor RO. So, what comment can you make? The gain is now minus GM times RL parallel RO. So, earlier in principle, what is the maximum incremental gain that you could get? No, I mean, if you had the freedom to change RL, what was the maximum incremental gain that you could get? Infinite. Earlier in principle, if you made RL an open circuit, the gain, the DC gain that you would get would be infinite. Now, what is happening? Even if you make RL infinity, the maximum gain that you can get is only minus GMRO. So, the maximum magnitude that of gain you can get is GMRO. This is often what is called the intrinsic gain of the device. Alright. So, it turns out that again this value of the intrinsic gain ideally of course should be infinity, but in practice this GMRO depends a lot on the details of the construction of the transistor. I mean, if you choose very short channel lengths, the GMRO can be as small as maybe 8 or 10. If you choose long lengths for the transistor, it can be as high as maybe 50, 60, whatever, right. So, you can see that the GMRO is not a is of the order of a few tenths, okay, that is what you can expect in practice. Alright. Now, the next thing we started looking at was various biasing techniques. Remember that the first robust biasing technique we looked at was the current mirror. So, this is some IREF. So, ideally regardless of the voltage Vx, as long as the transistor M2 is in saturation, right. What comment can you make about the current Ix is going to be IREF. But now there is a slight problem. So, if I plot Ix as a function of Vx, what curve should I expect? Pardon? Ideally, I should expect a constant like that, right. So, this is that VGS minus VT, okay. And what would this value be? What will that value be? Very good. All right. Now what happens in reality? What happens? It will be, there will be some slope, okay. So, at what value of Vx will the current exactly be equal to Iref? Okay, let me rephrase the question. You said there is a slope. So, it could be like that, it could be like that. What are we talking about? At what point? The question I am asking you is, first let us figure out at what point Ix will be equal to Iref. No? Why? Okay. So, the claim is that Ix will be exactly equal to Iref when Vx is exactly equal to Vgs, correct? Now, why does that make sense? M1 and M2 are identical, correct? Both of them have the same, gate potential. So, their drain currents will be exactly identical when the drain potentials are, because after all the current in the drain is a function of both the gate source voltage and the drain source voltage. So, if the two of them are, if the gate source voltage is the same as, I mean in both cases it is gate source voltage is of course constrained to be the same. So, if the drain source voltage is exactly the same for both M1 and M2, then you will have exactly the same current, correct. Now, what comment can you make about the, so if Vx increases beyond Vgs, do you think the current must increase or decrease? Increase, right. So, what will be the slope of the characteristic around Vgs, around Vx equal to Vgs? I hope all of you are able to see this, right. It's pretty straightforward. Around the operating point, the change in the current in the transistor due to the gate source voltage is fixed, correct, it is not changing. So, we are interested in the slope with respect to Vx. So, it is the slope will be the output conductance of the transistor, which is the ratio of this change in the drain current due to a change in the drain source voltage, which is 1 by, which is lambda times Iref, okay. So, this is an exaggeration. So, the curve probably looks something like that, okay. And this slope is 1 by right. So, this current source, which is ideally supposed to be a constant current, is now no longer a constant, it changes with Vx, because the output impedance is, the incremental output impedance of this current source is not infinite, it is finite. Okay. All right. Now, if you want, we just looked at just a little while ago. Okay. Anyway, let us do this. That we will come to this a little later. So, this is something to bear in mind. So, our current mirrors are not that accurate anymore. Okay. if you want the current mirror to be accurate, you have to absolutely make sure that the drain source potentials are also matched. All right. Then what else? Then we did the common drain amplifier. This is Vi. Earlier we had RL, and now with the new model for the transistor, what is the extra element we have? We have RO here, and therefore what comment can we make about the incremental output voltage? So all that you have to do is replace RL in earlier whenever you saw RL, now you replace it with RL parallel R naught. Okay. So the incremental gain, remember, was earlier, what was the incremental gain with finite GM? GM RL over GM RL plus 1. So if GM RL is much larger than 1, okay, what comment can you make about GM RL parallel R naught? Remember, GM R naught is a large number. So GM RL only. So as long as R naught is very large, GM RL is large, okay, and as long as RL is, R naught is much larger than RL, right, you will find that GM RL was a large number, it remains a large number. So the closed loop, the gain, incremental gain remains largely the same. Okay, so it's benign. So if earlier if RL was infinite, what comment can you make about the gain? Earlier, if RL was infinite, what was the gain? 1, right? Now even if RL is infinite, what will be the gain? GM R naught by 1 plus GMR. So if GM R naught is 50, then you will get 50 by 50. Okay, pretty straightforward. All right, the next thing is the voltage controlled current source. This is Vi. Okay, earlier what was the output resistance? Infinite. What is the input resistance now? Now earlier infinite. Okay. This is R. Now we have an extra here. This is RO. Let's call this Vx, and this is nothing but Gm times Vi minus Vx. All right, and this is the output port. So the first question to ask is, let's ask the question, what is the output resistance? To find the output resistance, what will we do? You set Vi to 0. So this becomes Gm times minus Vx, which is equivalent to saying this is Gm Vx. This is V test The question is, what is I test? Okay, before we do the math, should I test be positive, or should I test be 0, or should it be still 0? Should it be 0 or non-zero? Non-zero. Clearly now there's some connection between the drain and the source, right? So all right, so what is the unknown that we need to find? Vx. Okay, once we find Vx, we'll be able to find I test as simply being equal to easy way, Vx by R. All right, I test. Remember that this is still a Gaussian surface type thing, right? Whatever current is pulled out will be pulled out, will be coming out from the other side. So, so Vx by R must be equal to I test. The question is, what is Vx? So, you write KCL at the only node that is there, and what is that? Gm times Vx plus I test we write KCL. So, Vx by R plus Gm Vx plus Vx minus V test by R naught equals 0, which means that actually hold on, this is certainly something to do, but as I also like to illustrate a point here. So, in general, when you are trying to find the output resistance looking into a port, you can do it in two ways, right? You can either put a voltage, measure the current, or you can put a current and measure the voltage. Eventually, you should get the same answer whatever you do, but in I mean there will be cases where it is convenient to do one over the other, right? And this particular case happens to be one such case, right? What do we notice here? A whole bunch of arms are in series, correct? That this character here is in series with R, right? So, it is much, do you think it is easier to apply a voltage, measure the current, or push a current, measure the voltage? When things are in series, it makes a lot more sense to push current. So, that is what we will do. So, we will push I test. So, what is the voltage Vx? Well, what is the current flowing through R? I test. So, the voltage Vx is I test times R. So, what is the current flow? What is the output voltage V test? Gm Vx therefore is nothing but Gm times R times I test. So, the current flowing through R naught is I test times 1 plus Gm R. The voltage across RO is this times RO plus I test times R equals V test, correct. So, what is the output resistance? Is nothing but Gm times R naught plus R plus R naught. All right. Okay. Now, if you want to approximate it, remember in a Gm R naught is much larger than 1. Okay. So, comparing these two terms, which can we neglect? Sorry, between these two terms, which can we neglect? Gm R naught is much larger than 1. You can neglect the capital R. Okay. So, this becomes Gm R naught plus R naught. Now, in a good voltage controlled current source, what comment can we make about GMR? If you want to build a good voltage controlled current source, what comment can we make about GMR? So, GMR, if you are building a good current source, a voltage controlled current source, GMR is much larger than 1. So, which can you neglect here now? Gm times, all right. Is that clear? So, what comment can you make about the output resistance therefore? A sanity check. First of all, sanity check. This is the exact expression. What all sanity check can we run? Gm tends to infinity, Ro tends to infinity, okay, all right. Gm tends to, if R tends to 0, what should you get? You should get small r naught, that is indeed correct, all right. And small r naught tends to infinity, you must get infinite again, correct. All those cases we have seen earlier. So, if GMR and GMR naught are very large, the output resistance is simply Gm times GMR naught times capital R, or small r naught or r naught times Gm capital R. Okay. You can see therefore that the output resistance has been enhanced by this, the resistance looking in the drain is the resistance in the source multiplied by the GMR naught of this transistor. Okay. All right. So, basically the bottom line therefore is that the output resistance looking in here is approximately Gm times R naught, right. But the true thing is basically to this you need to add both R and R. Okay. All right. With that we will stop. We will continue in the next class.